Hello guys, how are you today? So today I'm going to be explaining the AP Chemistry Chapter 1 Interactions and Compounds course revision questions. So without further ado, let's get started. A 20-gram iron ball was heated to 70 degrees Celsius, so 20 gram was heated to 70 and dropped into a 200 milliliter beaker of water at 15 degrees Celsius. So they told us, describe the energy transfer occurring as the system advances towards thermal equilibrium. Now, first of all, what is thermal equilibrium? Thermal equilibrium is when both systems obtain the same temperature. A very common example would be when you're drinking something warm like tea or coffee or hot chocolate or something like this, you put your hands on the cup, and if your hands were cold, you'd feel the heat, right? And when you keep your hands on the cup for a long time, you will take your hands off and you will see that your hands have gained heat, whereas the cup has lost heat, or at some point they're gonna reach what? They're gonna reach the same temperature, right? And all of this happens, and it's called what? It's called thermal equilibrium. So now, look what's happening. We're dropping a 20-gram iron ball that is 70 degrees Celsius. It has a really high temperature. And then we drop it where? We drop it into a beaker containing water at 15 degrees Celsius. So logically speaking, heat is gonna go from the iron ball to the water. But if we want to say it in the terms of chemistry, we need to say that energy transfers. So energy transfers from the iron ball to what? To water. So that is it for question 1 part A. We'll move on to part B. Which object's temperature increases and which one decreases? For sure, the temperature that was initially highest will decrease and the one that was lowest will increase. So the water temperature will increase. So I'm going to write temperature of water increases, whereas temperature of ball decreases. Okay, this is something we need to know. We move on to part C. Compare the energy change occurring in the solid and in the liquid. What do they mean, compare the energy change? If we're taking them as one system, the iron ball and the water, we should know that whatever happens, the system, whatever energy it starts with, it will end with the same amount of energy, right? What does this mean? This means that potentially the energy lost by the iron ball, so I'm going to write energy lost by the iron ball should be equal to the energy gained by what? By the water. And since they are both in the same system, this is true. So when you're comparing two objects that have an energy change and they're considered in one system, right? You're going to say that the energy lost by this object should be equal to the energy gained by the other object. Why? Because the energy we start with should be the same as the energy we end with. Okay, so that is it for question part C. We'll move on to part D. Compare the average kinetic energies of the solid and the liquid once thermal equilibrium is reached. Okay, so what do we need to know? We should know that the average kinetic energy, I'm gonna call, this is average kinetic energy, so dash KE, okay? Average kinetic energy is directly proportional to the temperature. That means the more the temperature, the greater the average kinetic energy. The less the temperature, the lower the average kinetic energy. But they reach thermal equilibrium, meaning the temperature of the ball should be equal to the temperature of what? Of the water. So what does this mean? This means the average kinetic energy of the ball is equal to the average kinetic energy of what? Of the water. Okay, that's it. Very simply for part D. We'll move on to part E. Compare the final temperatures of the solid and the liquid once thermal equilibrium is reached. Well, logically speaking, we're talking about thermal equilibrium. That means the temperature of the ball should be equal to what? Should be equal to the temperature of the water. Okay, that's it for question number 1. We'll move on to question number 2. We need to classify each of the following processes as endothermic or exothermic. Endothermic means that it absorbs heat. Exothermic means what? Means that it releases heat. Okay, we'll move on now to part A. What does it say? The combustion of gasoline. What does it mean, the combustion of gasoline? Usually, when you stand behind the car, right? And there starts to happen the combustion and you see out of the... So like from the engine, right? The combustion of gasoline occurs and then you will feel like the gas or the smoke come out and you feel that it's what? It's warm. What does this mean? Okay, let me explain something before we continue. When I say absorbs heat, the temperature of the reaction itself increases, but the temperature of the surroundings, what happens? It decreases because you're taking heat away from the surrounding. And same applies to exothermic. If I am releasing heat, the temperature of the reaction is going to decrease because it's losing, right? It's losing energy. Whereas the temperature of the surroundings is going to increase because there's heat being added to it. So the combustion of gasoline, I'm not touching the reaction itself. I'm not feeling the reaction itself. I'm feeling the surroundings. So if the surroundings are warm, then what can I say? I can say that it is an exothermic reaction. The thermal decomposition of calcium carbonate. Whenever we encounter decomposition, so whenever we see decomposition of something, usually what's decomposition? You have a substance and then it decomposes or it breaks down. In order for it to break down or break the bonds, what does it need? It needs energy. So of course it's gonna absorb the energy. So that's why it's endothermic. Photosynthesis, logically speaking, if you take biology, or even if you took biology since grade 5, you would know that photosynthesis requires sunlight, right? It absorbs the sunlight, so it's absorbing energy. What does this mean? This means that it is endothermic. Now, the condensation of water vapor on a cold surface. What does this mean? This means it was initially a gas, and the gas has a very high speed, and it does not have any LDF forces, barely any. And then it condenses. What's happening? If it did not have any LDF forces and then we condensed it to form water vapor, to form liquid water, right? Which has London dispersion forces, right? Which has hydrogen bonds, which has forces. So what are we doing? We are changing it from something that does not have any bonds into something that has bonds, right? So in order to do this, or in order to form the bonds, we need to release energy. But the reaction needs to release energy. So when it releases energy, it is exothermic. We're going to move on to question number 3. What does it say in question number 3? A 23-gram sample of ethanol was constantly heated while its temperature being measured. Okay, the heating curve was plotted as shown. Answer the questions knowing that the molar heat of fusion of ethanol is 5.02 kilojoules per mole. And the molar heat of vaporization of ethanol is 38.6 kilojoules per mole. So part A, how much energy is needed to vaporize the 23-gram sample of ethanol at 350 Kelvin? So I need to look back up to what I have over here. I have what? I have fusion of ethanol, vaporization of ethanol. They wanted what? They wanted to vaporize. So I'm going to only look at the vaporization of ethanol. I'm going to see the unit is kilojoule per mole. That means I need to have something that contains kilojoule and something that contains mole. I'll go down again. They want the energy, and you should know that energy is always in kilojoules. So we need to find the thing with kilojoules. And what did they give us? They gave us the mass of oh my goodness, did I say math? My bad. The mass, okay, of ethanol. Sorry, because I'm talking too much, I mix up my words. So the mass of ethanol, which is 23 grams, okay? And then the molar mass of ethanol, we can find it. What's the molar mass of ethanol? First of all, what is ethanol? Ethanol is an alcohol, but we have 2 carbons, right? And we also have what? We also have OH, you don't forget about that. And we have what we have on the remaining bonds, hydrogen, right? So basically, I need to find my calculator 1 second. So I have 2 carbons, so 12 times 2. And I have 5 hydrogens, so plus 5 and 1 oxygen, so 16. I have 6, my bad. I have 6 hydrogens, so 16 plus 1, right? So again, 12 times 2, and then 6 times 1, and then 16. You add them all together, you're going to get what? You're going to get 46. Okay, and then they gave us what? They gave us the temperature to be 350 Kelvin. We don't really need the temperature because we know that the C we are dealing with, or not the C, sorry, the delta H of vaporization that we are dealing with is 38.6 kilojoules per mole, right? And now I need to find what? I need to find my energy in kilojoules. So Q equals what? Equals the number of moles, which is mass over molar mass, times what? Times delta H. I'll put it on my calculator. I'm gonna get 23. So 23 over 46 times 38.6, which will give me my answer to be 19.3 kilojoules. So that's it for part A. We'll move on to part B. What does it say? In which state does ethanol exist in section S? Section S is where? Section S is here. This you should know it from grade 9 or grade 10. Initially, we start as a solid. And it starts increasing its temperature slowly, slowly, slowly. And then, when it becomes flat, it's a solid and a liquid. And then, here, it will become only what? It will become only a liquid. When it starts increasing, it's only a liquid. And the temperature is increasing slowly, slowly, slowly. And then here, what is it? It's a liquid and a gas. And then once it reaches here, it becomes a gas. And the temperature keeps on increasing and increasing and increasing, right? So if they're telling us about section S, it would be what? It would be a liquid plus a gas. They said, explain why despite being heated, the temperature of ethanol in section Q, where section Q here, stays the same or remains the same. This is a really good question. Why, when we are heating at section Q, where it exists both as a solid and liquid, right? Why even when we are heating, the temperature stays the same? This is really, really, really important. Very simply, you're gonna say that the energy is used to break the intermolecular attractions between molecules in the solid. So between molecules in the solid, right? So again, let's think about it again. Why, despite being heated, the temperature of ethanol in section Q remains the same? In section Q, it exists as a solid and a liquid. Why does the temperature stay the same? Very simply, because the energy we have is used to break the intermolecular forces between the molecules in the solid, or the intermolecular attractions between the molecules in the solid, and this will cause what? This will cause it to change the state, and thus it will end up being a liquid where it will end up being a liquid at R. And this is why the temperature stays the same. We'll move on to part D. What does it say? Describe what happens at the particle level that results in section S being much longer than section Q. Why is section S longer than section Q? This is actually really important. Actually, if you go up and you compare the vaporization, which is section S, and the fusion, which is section Q, you will see that section S, the heat of vaporization is much greater than the heat of fusion. Why is this? They're asking us to explain why this is. Very simply, you say the enthalpy of vaporization is always larger than the enthalpy of fusion. Why? Because separating the molecules completely from the liquid to form a gas requires much more energy and time than separating molecules from their fixed position in the solid state to a liquid state that only requires breaking a fraction of the intermolecular forces. So again, this is really important, really, really important. What they are saying? They are saying that why is the molar heat of vaporization greater than that of fusion? Very simply because when we are dealing with melting, or the heat of fusion, right, we are breaking some of the intermolecular forces. So that's why it requires less energy and it takes less time. Whereas when we're doing vaporization, meaning we're going from liquid to gas, right, we require much, much more energy because we're breaking all of the bonds or all of the intermolecular forces. Okay, so that's it for question part D. I explained it orally. What is the melting point of ethanol? How do you find the melting point? So very simply, go back, sorry, my bad. The melting point of ethanol in degrees Celsius. If you check here, your temperature is in what? Your temperature is in Kelvin. So I'm going to go over here, right? I'm going to say that this is the melting point in Kelvin. So it's going to be 150. How do I know? I got it from the graph. Now I need to change it from Kelvin to degrees Celsius. So I'm going to subtract 273. So 150 minus 273. This would give me minus 123 degrees Celsius. Okay. So that's it for what? That's it for part E. We'll move on to part F. So part F, explain why the slope of section T is greater than the slope of section R. This is a really, really, really good question. We should know that the C gas, specific heat capacity, something we need to relate it to, of the gaseous ethanol is much, much less than the specific heat capacity of the liquid ethanol. So what you need to write in the periodic, okay, or what you need to state is that the specific heat capacity of ethanol as a gas is much less, okay, or is less than the specific heat capacity of what? Of ethanol as a liquid. What does it mean? It means that we require less energy to raise the temperature, right, of 1 gram of gaseous, I forgot how to write gaseous, gaseous ethanol by 1 degrees Celsius, right? So, again, how are we gonna explain this? In the exam, you go and you start saying, the specific heat capacity of ethanol as a gas is less than the specific heat capacity of ethanol as a liquid, right? That means we require less energy to raise the temperature of 1 gram of gaseous ethanol by 1 degree Celsius than needed for liquid ethanol. And that's it for this question. We finished question number 3. We'll move on to question number 4. What does it say? Reaction pathway diagram gives information about reaction enthalpies. Identify the diagram that represents an endothermic chemical reaction and the diagram that represents an exothermic reaction. So, the first one is exothermic. The last one is what? The last one is endothermic. How did I? Logically speaking, we know exothermic means that the reaction will release energy. What does this mean? This means that the energy of products is much less than the energy of reactants. Whereas in the endothermic, we know that the reaction is absorbing energy. That means the reaction of the products is much greater than the reaction. The heat of the products is much greater than the heat of the reactants. Okay, so that's it for question 4A. We'll move on to part B. Give below the reaction pathway diagram for a specific reaction. Now part B. Given below the reaction pathway diagram for a specific reaction, identify the label that corresponds to each of the following. First thing is activation energy. Which of the following corresponds to activation energy? Activation energy corresponds to what? Corresponds to X. So when I'm talking about activation energy, it's the heat from my reactants to what? To my products. Or sorry, not to my bad, not to my products, my bad. When we're talking about activation energy, it's the heat from the reactants all the way to where? All the way to the top of the peak. Then this is what? This is X. And this is going to be what is going to be my activation energy. Whereas the enthalpy of reaction is the heat between my products and my reactants. So in this case, it's what? It's Z. Okay, we're going to move on now to question number 5. What does it say? Consider the reaction to A plus B will give me A to B, whose reaction profile is shown below. Describe the flow of heat occurring when 1 mole of A to B is formed. Is that it? So describe the flow of heat occurring when 1 mole of A to B is formed. Very simply, I can't talk today, my bad. Very simply, not very simply, very simply. So again, when 1 mole of A to B is formed, what's the energy change? We go from 100 to 180. So what am I going to do? I'm going to do the products, right? The products heat, which is 180, minus the reactants heat, which is 100, and I'm left with 80 kilojoules. On top of that, I know it's what? It's endothermic, so I need to put plus 80 kilojoules. Now, to describe it, I say that the reaction is exothermic, so 80 kilojoules are transferred from the surrounding into what? Into the system. So the surrounding loses heat, but the system gains heat, okay? We're going to move on to question number 6. What does it say? Identify the type of enthalpy change of reaction in the following chemical equations. For reactions that are not combustion, delta HC, formation delta HF, or neutralization delta H neut, classify them as delta H of reaction. So basically they said you should what? You should identify the type of enthalpy change happening, okay? Meaning it should be either delta H of combustion, delta H of formation, or delta H of neutralization. If you don't know what it is, you say it's delta H of reaction. So here I have what? I have an acid and I have a base. What does it give me? It gives me a salt and it gives me water. This is a classic what? A classic neutralization reaction. So this is delta H neut. I move on to part C. Carbon plus oxygen gives me CO2. This is combustion. Anything that you added to oxygen is what is combustion. So delta HC. On top of that, we're forming something. So it's delta HF. So you say it's both delta H of combustion and delta H of formation. On top of that, we'll move on to part C. What does it say? H2CO3, okay? So I'm dealing with H2CO3, which is an acid, right? CaCl2, which is a salt, and CaCO3, it will give, and it gives me what? It gives me a base in addition to what? In addition to an acid. So we did not take any reaction like this. I don't know what type of reaction this is. I'm just going to call it what I'm going to call it, delta HR. So that's it for section 1.1. We'll move on now to section 1.2. We'll move on to 7 grid. What does it? So we start with question 7. 100 centimeter cubed, I'm going to change it to decimeter cubed, so 0.1 decimeter cubed, of 1 molarity HCl was mixed with 100 centimeter cubed, so 0.1 decimeter cubed of 1 molarity NaOH aqueous. At what? At 20.10 degrees Celsius in a coffee cup calorimeter. So I have V1, C1, V2, C2. I have temperature, okay? The maximum temperature recorded due to the reaction was 26.1 degrees. So temperature initial, temperature final. Assume that delta H for the reaction, they gave us the balanced equation. H plus aqueous plus OH minus will give us H2O. Assume the density is 1 gram per centimeter cubed, then specific heat capacity is this. So from all of this, they want us to find what? They want us to find delta H. I will look at what? I will look at the unit of my specific heat capacity. It is joules per degrees Celsius times gram. What does this mean? This means that my answer, first of all, delta H needs to be in joules, right? But that means I'm also going to be using what? I'm going to be using temperature, and I'm going to be using what? I'm going to be using mass. So, actually, delta H is in kilojoules, but Q, what we're looking for, is in what? Is in joules. Q is in joules, right? And Q is equal to MC delta T, right? I have what? I have the density, okay, of the solution. I have HCl and NaOH, right? I have their ratios. They gave it to me over here. It's a 1 to 1 to 1 reaction, okay? So what does this mean? This means I'll be able to find the volume of water. So 100 centimeter cubed initially was added to another 100 centimeter cubed. Together combined, they will form 200 centimeter cubed of water, right? Now, why do I leave my volume in centimeter cubed? Because if I look over here, it's in centimeter cubed. So Q is equal to M times C times delta T. I don't have M, but I know that mass is equal to density times volume. I have my density, which is 1. I have my volume in centimeter cubed, which is 200. I have C, which is 4.2. I have the change in temperature, which is how much? The change in temperature, which is 6 degrees. So I put it on the calculator. 1 times 200 times 4.2 times 6. This will give me an answer, which is what? Which is 5... Sorry, it is 5040. Perfect. So now I have the value of Q, but do they want Q? No, they want delta H. We know delta H is what? Delta H is equal to minus Q over N. I have my Q, which is 5040. So minus 5040 over N, which is what? Which is the number of moles. How do I find the number of moles? That's a really good question. I just need to find my limiting reagent. How do I find my limiting reagent? I will say this is 0.1 decimeter cubed times 1. So this is 0.1 mole. Okay? So let me take it as H plus. So H plus will give me 0.1 mole. Here, again, 0.1 decimeter cubed times 1 molarity. So this will give me what? This will give me 0.1 mole. So if from both of them I got 0.1 mole, how will I find the limiting reagent? I will do the number of mole over the coefficient versus the number of mole divided by the coefficient. So 0.1 divided by 1, 0.1 divided by 1. I will get what? I will get the same ratio. That means they're both the limiting reagent, or there is no limiting reagent, right? So now what does this mean? I can take any one of them and I can solve the whole equation from it. So I would say 1 H plus gave me 0.1, 1 OH minus gave me 0.1. How much will 1 H2O give me? 1 H2O will give me 0.1 mole. So now I have what? I have the number of moles, which is 0.1. I will get delta H to be equal to minus, let me fix that a bit. Delta H is minus 50400, right? But this is in what? This is in joules per mole. So I need to change it into what? I need to change it into kilojoules per mole. So I will divide it by 1000. So divided by 1000. And I will get an answer of what? I will get an answer of minus 50.4 kilojoules per mole. That's it for question number 7. We'll move on now to question number 8. What does it say in question number 8? A 1.15 gram sample of ethanol. What's the molar mass of ethanol? It's 46. You guys should know how to calculate it, right? Was burnt in a bomb calorimeter and was found to raise the temperature of 100 centimeter cubed, so 0.1 decimeter cubed of water by how much? By 80 degrees. So I had plus 80 degrees Celsius, right? Now, they gave me the specific heat capacity of water, which is 4.18 joules joules per gram times degrees Celsius. Okay, what's the first thing they asked for me? First thing they asked from us? Calculate the number of moles of ethanol that were burned. How do I calculate the number of moles of ethanol that were burned? First of all, I know that I have the mass of ethanol. I know the molar mass of ethanol. Oh, I moved it all. It's fine. I have the molar mass of ethanol. There we go. So for sure I'll be able to find the number of moles. Number of moles is mass over molar mass, right? So what's the mass in this case? It's 1.15. What is the molar mass? It's 4.6. So you put it on the calculator, you will get 0.025 mole, but they wanted 3 significant figures, so 0.0250 moles. We'll move on to part B. What does it say? Calculate the heat change Q, okay, for the experiment. How do I find the heat change Q? Q is equal to, based on the equation, I have C to be what? To be 4.18 joules divided by grams times degrees Celsius. So Q is equal to what? I have grams, so M, I have what? I have C, and I have my change in temperature. So Q is MC delta T. But now, Q is the heat change. When you're burning something, are you changing the temperature? No, you're not. However, what happens was that it raised the temperature of water. So water, okay, is the thing we're gonna be dealing with. We know that water has a density of 1 gram per centimeter cubed. That means in this scenario, what is the mass of water? It's gonna be 100 centimeter cubed times 1 gram per centimeter cubed, which is what? Which is 100 grams. So this is what? This is the mass of water. So 100 grams times 4.18 times the change in temperature, which is 80. You put it on your calculator. And you're gonna get 33440 joules, but I need it in kilojoules, so I'm gonna divide by 1000. And it's gonna give me to 3 significant figures, 33.4 kilojoules. So my answer over here is 33.4 kilojoules. We'll move on to part C. They said calculate delta H of combustion. Okay, so let's go up and see the given again. C2H5OH was burnt and raised the temperature of water by 80 degrees Celsius. So now what I can see over here is that they're helping me build up my equation. They told me to find the moles of ethanol. They told me to find Q, okay, of the experiment. So now what am I gonna do? To find the experimental molar enthalpy change of combustion, what am I gonna do? I'm gonna do delta H is equal to minus Q over N. So minus, minus 33.4 divided by what? Divided by the moles of ethanol. So you put it on the calculator and you're gonna get an answer to 3 significant figures to be minus 1340. Okay, so now we'll move on to question. So now we move on to question number 9. What does it say? It says a 7 gram sample of potassium hydroxide KOH is dissolved in 100 centimeter cubed of water. The temperature increases from 25 to 42. Determine the energy released from dissolving this amount of KOH. When they say the energy released, that means they're referring to Q. So they did not ask you for the change in heat or the delta H. They're asking you for the energy, Q. Now, let's see what I have in front of me. I am given the mass. I can find the molar mass of KOH. How much is the molar mass of KOH? Molar mass of KOH is approximately 56. Dissolved in 100 centimeter cubed of water. That means the mass of water is how much? Is 100 grams. Again, I explained that mass is equal to density times volume. My density is 100 centimeter cubed. My volume, sorry, I mixed them up. My density is 1 gram per centimeter cubed. My volume is 100 centimeter cubed. So the mass is gonna be 100 grams. Okay. The temperature increases from 25 to 42. So delta T is 42 minus 25, which is 17, right? And now they want us to find Q. Okay. Now, when we're finding Q, we're thinking about the reaction. In this case, okay, what is the object that changes temperature? It's not KOH that changes temperature. Instead, it's water. So now what we're going to do is we're going to take the mass of water, which is 100 grams, multiply it by the C of water, which is 1.48, and multiply it by what? Multiplied by the change in temperature, which is 17. You're going to get approximately 7.1 times 10 to the power of 3 joules, so 7.1 kilojoules. We're going to move on now to question number 10. What does it say in question number 10? Calculate the amount of heat needed to melt 6 grams of solid magnesium originally at 27 degrees. So this is what this temperature initial. Now we need to pay attention. The amount of heat needed to melt 6 grams of solid magnesium originally at 27 degrees. So first thing that we need to do is we need to let solid magnesium reach its melting point. In order for this to happen, we need a specific amount of energy. So this is the energy needed to reach melting point. On top of that, we need to find what? We need to find the Q that is needed to what? Needed to melt. So we need to find what? We need to find two different Qs, and then we're gonna add them together. So now what do we have? We know that to go from temperature initial to temperature final, okay? We're gonna do from 650 degrees Celsius to 27. We have a delta T of how much? Of 623. Now, it's in Kelvin. Do we need to change anything? No. Because whether you have it in degrees Celsius or Kelvin, you're gonna end up with what? You're gonna end up with the same exact result. Now, what am I gonna do? I'm gonna find, okay, with the equation that contains delta T, the energy needed to reach the melting point. So it's gonna be Q equals MC delta T. It's gonna be the mass, which is 6 grams. Oh, but I do have a problem over here. My C, my bad. You see, you should read. Don't do like me and like go jump directly into the question. My C is in joules per mole times Kelvin. What does this mean? This means they want the moles. That means it's gonna be NC delta T. So please again pay attention to the units. So mole, so joules per mole times Kelvin. So NC delta T. So it's gonna be mass over molar mass. So 6 over what's the molar mass of magnesium? It's 24 times 24.9 times delta T, which is 623. So on the calculator, this will give me an answer which is approximately 3878 joules. Perfect. Now for the second part, they need the Q needed to melt. What is the Q needed to melt? The Q needed to melt is the molar heat of fusion, right? Now what do I see? I see that my unit is only mole. So what does this mean? This means it's gonna be the Q, which is in kilojoules, is gonna be my number of moles, right? Multiplied by what? Multiplied by delta H of fusion. Okay? So in this scenario, what's my number of mole? It's 6 over 24 times 8.7. What is it? 24, 8.7, right? So you put it on the calculator. 6 over 24 times 8.7. You're gonna get an answer, which is what? Which is 2.175 kilojoules. So now I need to add them together. So Q1 plus Q2, that's gonna be 2.175 kilojoules plus 3.878. You add them together, and you're gonna get an answer to the correct number of significant figures, which is 3, because the smallest significant figures is 3. So that's gonna be 6.05 kilojoules, okay? We're gonna move on to question number 11. What does it say in question number 11? 4 different substances of the same mass at room temperature. Okay, question number 11. 4 different substances of the same mass at room temperature each absorb 700 joules of heat. Okay, first thing, we know that they're at the same mass. And they each absorb what? They each absorb the same amount of energy. They gave us the substance and they gave us their specific heat capacity. Right? And we know that the equation is Q equals MC delta T. If they have the same mass, they have the same joules, right? And we're dealing with C and delta T. We can say that C is inversely proportional to delta T. What does this mean? This means the greater your C, the smaller your delta T, okay? So, in which substance is the smallest change in temperature? You're gonna say the four samples are of equal mass, therefore the substance with the greater specific heat capacity will experience a smaller change in temperature, okay? So, in this scenario, which one has the greatest heat capacity? Lithium. So, lithium will have what? Will have the highest, it has the highest specific heat capacity, but it will have what? It will have the smallest change in temperature observed. We'll move on to question number 12. What does it say in question number 12? Question 12. A chemical reaction studied using calorimetry has the enthalpy profile diagram shown below. We have reactants have a greater enthalpy than products. What does this mean? This means energy is released to the surroundings, right? That means the temperature of the reaction decreases. What does this mean? This means that it is an exothermic reaction. So given that delta T represents the change in temperature of water in the calorimeter, what can be deduced from the diagram? First thing we can deduce, okay, is that because the reaction is exothermic, it will release heat, right? When it releases heat, it will increase the temperature of water. So delta T, which is different than delta H is negative. But however, delta T, which is the temperature of water, is going to be what? It's going to be positive, because delta T is the change of water, the change of temperature in the surroundings. Delta H is the change of temperature in the reaction. So if it's exothermic, that means the water is going to gain the energy and it's going to increase in temperature. Another thing we can deduce... Oh, well, yeah, that's pretty much it. I just explained everything. That's it for question 12. We'll move on to question 13. What does it say? Question number 13. What does it say? 2 bomb calorimeters are set up as shown below to compare the energy content of 1 gram of each of the two fuels, given that the specific heat of water is 4.2 joules per gram times degrees Celsius. Which of the two fuels has a greater energy content per gram? So our keyword here is what is per gram. So in this scenario, what do we need to see? What do we need to see? We see that we have the energy of the fuel, right? The energy of the fuel will change the energy of the water. What does this mean? This means that Q of the fuel is equal to Q of the water, so it's equal to mass of the water times C times delta T. What's the mass of the water? Did they give us the mass of the water? Wait, let me find it. Yeah, 500 grams. So 500 times C of water, which is 4.2, times delta T, which is the change in temperature, which is 10. So here, this will give me 21,000 joules per how many grams of fuel? Per 2 grams of fuel. So you divide it by 2, and you're going to get what? You're going to get almost approximately 11,000. Actually, let me put it more accurately. 1,0500 joules, okay? Now over here it's the same thing. Q fuel equals Q water equals M of water times C times delta T. So 3,000 times C of water, which is 4.2, times delta T, which was how much? Which was 10. This should give you an answer of 13,000? No, 130,000, my bad. 130,000 joules, right? But this is per 15 grams. So you're going to do 130,000 joules divided by 15 grams. This will give you 87. Is it 87? No, not 87. Yeah, 8,700 joules, right? So which one is smaller? 10,500 or 8,700? For sure, the 10,500. So what does this mean? This means that fuel 1, or the combustion of 1 gram of fuel 1, releases more energy than the combustion of 1 gram of fuel 2. Now we move on to section 1.3, which is Hess's law. So this is Hess's law. Identify X in the given energy cycle. Let us see. Here we have delta H of formation of what? Of H2O liquid. This is what we're focusing on, right? Right, and over here it's the delta H of formation of CO2. X would be what? X would be... So here, look what we have. We have oxygen, oxygen. Can we form oxygen? No, we cannot form oxygen. So we never ever say the delta H of formation of an element. We cannot form an element. So you will say that this is the enthalpy change of formation of glucose, or delta H of formation of glucose. We move on to question number 15. An energy cycle for the reaction between magnesium and aluminum oxide is given below. Find the expression that determines the delta H of formation of MgO from the cycle. Okay, this is the cycle, Hess's cycle. This is for AS, not AP. We'll move on to question number 16. Calculate the standard enthalpy change for the following reaction in kilojoules per mole. How do you find the standard enthalpy change? This is the standard enthalpy change of formation. When it's the standard enthalpy change of formation, you're going to do the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants, and don't forget to multiply by what? By the number of moles. So, it's gonna be for the products, so 16 times minus 394 plus, don't forget your brackets, they're really important, plus 18 times minus 286, right? Then I'm gonna close my brackets, minus what? Minus the delta H of formation of the reactants. You don't have any formation for elements, so you remove the O2. So minus 2 times the delta H of formation of C8H18, so minus 269. You put it on your calculator, you should get an answer which is, let me put it on my calculator. You put it on the calculator, you will get an answer, which is what? Which is to the correct significant figures, which is 3 minus 1, 0, 900. That's question number 16. We'll move on to 17. Use Hess's law to calculate delta H for the reaction. How do we use Hess's law? Okay, basically, look what I like to do. I like to say, I have this as a reactant, so everything in yellow is a reactant. Everything in red is what is a product. So from what I have, I should have my yellow to be exactly the same reactants and my red to be exactly the same product. So let me start with my reactant. This over here should be on the reactant side. So I'm going to multiply it by minus 1 to change it to the reactant side. But I also need to have it to have a coefficient of 2, so I'll multiply it by 2. So minus 2. Next step. What do I have for my reactants? I have carbon. Here, carbon is already on the reactant side. The only thing I need to do is to multiply it by 3. Now, when I multiply the whole equation, I'm going to get this. Okay? And I'm going to get what? I'm going to get 2Fe2O3 in addition to, 2Fe2O3 will give me 4Fe plus 3O2. Now, look. If you have two exactly the same on opposite sides, you can subtract. So 3 minus 3, that's 0. And I'm left with what? I'm left with 3 carbon plus 2Fe2O3 will give me 4Fe plus 3CO2, right? So now look what I'm going to do. I'm going to multiply 3 by what? I'm going to multiply 3 by this. So it's going to be 3 times minus 390. In addition to, I'm going to multiply minus 2 by this. In addition to minus 2 multiplied by minus 820. You put it on the calculator and you should get an answer. Which is what? You should get an answer which is to the correct number of significant figures. Because as you can see, like this, 470 point. Okay? Or you could write it as 467 kilojoules. We'll move on to question number 18. What does it say? Extracting iron from iron ore involves the following reaction. 2Fe2O3 solid plus 3 carbon solid will give me 4Fe solid plus 3O2. The standard enthalpy formation of this is this. Okay, so what do they want? What is the enthalpy change during the production of 2.5 moles of iron? Very simply. 4 iron gives me a certain amount of enthalpy change, and then I'll be able to find the enthalpy change during 2.5 moles of iron. Okay. So now let us find the enthalpy change of formation. First of all, I have Fe2, this is enthalpy change. Okay, so it's gonna be what? It's gonna be the reactants are here, the products are here. So enthalpy change during production is the change or the sum of the number of moles multiplied by delta heat of formation of products minus the sum times the number of moles times delta heat of formation of what? Of the reactants, right? So delta H of formation of the products, which in this case is 3 times minus 393.5 minus the one of the reactants. You only use the ones that they gave it to you because look, these two are elements, they're not going to have anything of formation, right? So minus 2 times minus 824.2, you'll get an answer, which is what? You'll get an answer which is 467.9 kilojoules per mole. Now, if I need that to be for 2.5, if 4 gave me 467.9, right? How much will 2.5 give me? So 4 gave me 467.9. 2 will give me how much? You do cross multiplication. So then it's gonna be 2 times 467.9 divided by what? Divided by 4. This should give you my bad, this is 2.5. Sorry, I messed up a lot. 4 gives you 467.9. So how much will 2.5 give you? This would be cross multiplication. So 2.5 times 467.9 divided by 4. So to the correct number of significant figures, 292 kilojoules per mole. Okay? Or not per mole, just kilojoules. Okay, here instead, this is kilojoules per mole of what? Of reaction. Anyways, let's move on to question number 19. What does it say? So we move on to question number 19. What does it say? It says formaldehyde CXHYO is used to inactivate viruses in the process of vaccine manufacturing. The complete combustion of a 2.50 gram sample of formaldehyde and excess oxygen produces 3.67 grams of carbon dioxide and 1.50 grams of water, specific heat capacity. So here, I'll be able to find what? I'll be able to find the percentage of carbon dioxide produced, the percentage of water produced, right? Or not necessarily the percentage, the number of moles, my bad. And then I'll also be able to find the number of moles of oxygen produced. And all of this will lead me to find what? Will lead me to find the molecular formula. So let's start. I have carbon, hydrogen, oxygen, right? So first thing I'm going to do is I'm going to find the mass of carbon and the mass of hydrogen, right? So what is the mass of carbon? The mass of carbon in this scenario. First of all, I'm going to take carbon dioxide, right? I'm going to take 3.67, the mass. Divided by what? Divided by the molar mass. What's the molar mass of carbon dioxide? 44. So 3.67 divided by 44. I'll multiply it by now. How many carbons do we have in carbon dioxide? By 1. And then I'll multiply it by what? By the molar mass of carbon, which is 12. So I get the mass of carbon to be what? To be almost 1 gram. For hydrogen, it's going to be 1.50 divided by 18. I have 2 hydrogens, right? So I'm going to multiply by 2 times the molar mass of hydrogen, which is what? Which is 1. So you put it on the calculator, you're going to get 0.167. So you have 0.167. And now you can find the mass of oxygen. How do I know the mass of oxygen? It's a 2.5 gram sample of formaldehyde. So 2.5 minus 1 plus 0.167. I will be left with 1.333. This is the mass of oxygen. Next step I'm going to find the number of moles. So mass over molar mass. So for carbon, it's 1 over 12. That's going to be 0.083. Right? For hydrogen, it's going to be 0.167 divided by 1, which is 0.167. For oxygen, it's going to be 1.3333 divided by what? Divided by 16, which is what? Which is also 0.0833, right? Now, from this, what am I going to do? I'm going to divide by the smallest ratio, so 0.0833, 0.0833, 0.0833, and I'll be left with a ratio of 1 to 2 to 1. So what is the molecular formula of formaldehyde? It is CH2O. That's it for part A. We'll move on to part B. The standard enthalpy change of combustion of formaldehyde in the data book is greater than the value calculated from the experiment. Mention 2 reasons responsible for this deviation. So one deviation could be that the experiment is not done under standard conditions. So experiment is not done under standard conditions, right? And another one would be that not all formaldehyde undergoes complete combustion. And another factor is that heat is what? Heat is lost to surrounding. Heat loss to surroundings. So 3 possible reasons, okay? that the standard enthalpy change of combustion of formaldehyde in the data book is greater than the value obtained is because maybe experiment is not done under standard conditions, or not all formaldehyde undergoes complete combustion, or there is heat loss to surroundings. We'll move on to part C, construct. Okay, part C, construct a Hess cycle. We don't have to do this. They just want the standard enthalpy change of formation of formaldehyde, right? And they gave us the combustion. What you need to know is that to find the delta H of formation of any compound, it's equal to the sum of number of moles multiplied by the change in the heat of combustion of the elements minus the sum of the number of moles times the change in heat of combustion of what? Combustion of the compound, right? So in this scenario, the delta H of formation of formaldehyde would be minus 394 plus minus 286, right? Actually, let me write the balanced equation, my bad. I forgot to write the balanced equation. Here it's carbon plus H2 plus half O2 will give me what? Will give me formaldehyde, which is CH2O. Now, all of them have enthalpy change of combustion except oxygen. Why? Because oxygen cannot burn. Why? Every single thing in this universe burns in the presence of oxygen, but oxygen in the presence of oxygen does not burn. That's why it does not have an enthalpy change of combustion. So what do we say in this scenario? We find these. So minus 394 minus plus minus 286. All of this minus what? Minus 571. I put it on the calculator, I'll get an answer which is minus 109 kilojoules per mole. We'll now move on to question number 20, which is bond energies and enthalpy changes. So for question 20, I always prefer to draw what we have. So we have N, triple bond N. You guys should know how to draw it by now. Then we have 3 times H single bond H. Will give us what? Will give us 2 times N H3, so 2 times NH3, like this. Perfect. So I have 1 N triple bond N, so that's 941. Okay, so this is 941. Then I have 3 times H single bond H, so 3 times 432, so 1296. And then I have 2 times 1, 2, 3, NH. So 2 times 3, that's 6. 6 times N single bond H, so 391. This will give me an answer of 2346. So now what am I going to do? I'm going to do reactants minus products. Why? Because this is bond energy. So it's the sum of the bonds broken minus the sum of the bonds formed. So reactants minus products. So 941 plus 1296 minus 2346. You put it on the calculator. You will get an answer which is what? Which is minus 109 kilojoules per mole. We'll move on to 21. 21 is quite long, and then 22, and then we're done. I don't do the top questions. I'm thinking I may do a video of only top questions, but that would be for tomorrow. But yeah, other than that, I'm gonna continue 21, 22, and then I'm done with this video. So dimethyl ether, a flammable gas, has the following structure. Dimethyl ether undergoes a complete combustion according to the following reaction. Calculate the value of standard enthalpy change of combustion of the reaction. So look what I'm gonna do. I have this plus 3 times O2O double bond O, right? Will give me what? Will give me 2 times CO2, so CO2 is like this. Okay? Plus 3 times H2O. H2O is like this. Single bond, my bad. Yeah, it's like this. Right? So now I have the bonds drawn in front of me. I'll be able to imagine. So here the same thing we need to do to find the change for combustion. Reactants minus products. Okay? They gave me bond energy, so of course I need to do bonds broken minus bonds formed. So that means I'm gonna take, here I have carbon, oxygen. Okay, 2 carbon, oxygen. So what does this mean? First of all, I have 2 times carbon single bond oxygen, so 2 times 336. Plus 1, 2, 3, 4, 5, 6. Plus 6 times C single bond H, so 410. Okay, in addition to what? In addition to 3 times O double bond O, so 3 times 496. All of this minus what? Minus 2 times C double bond O, which is 805. right? Plus what? Plus 3 times 2. So, sorry, 3 times, here we have what? Sorry, here this is also wrong. This is 2 times 1, 2, so that's 4 times 805. And then here this is 3 times 1, 2, that's 6 times O single bond H, which is 465. So you put it on your calculator, okay? That's gonna be, I think this is 2. So 2 times 336 plus 6 times 410, okay, plus 3 times 496. All of this will give me 4620, right? Minus what? Minus 4 times 805 plus 6 times 465. This will give me 6010. You put it on the calculator. So 4620 minus 6010. This will give me an answer, which is what? Which is minus 1390 kilojoules per mole. We move on to part B. What does it say? It says define the term exact bond energy. Exact bond energy is the energy required to break a specific covalent bond in a particular molecule in the gaseous state. So, exact bond energy is the energy required to break a specific covalent bond in a particular molecule in a gaseous state. We move on to part C. Explain why using exact bond energies instead of average bond energies gives a more accurate values. So why do we use exact bond energies instead of average bond energies? Very simply, the average bond energy for a specific bond is a value averaged from different molecules, whereas exact bond energy takes into consideration the environment of the bond. So, a more accurate value is obtained when using the exact bond energy. So basically, in the example, you say the average bond energy is a value averaged from different molecules, whereas exact bond energy takes into consideration the environment of the bond. Thus, the exact bond energy would be more accurate. Okay, we'll move on to part D. What does it say? Another method to determine enthalpy changes using Hess's law. So what do they want us to find? Okay, we need to keep this equation in mind. Let me keep this equation in mind. What's this equation? So I'm going to go back down and I'm going to write the equation that we need. What's the equation that we need? We need C2H6O gas plus 3O2 gas will give me what? Will give me 2CO2 gas plus what? Plus 3H2O liquid. Now I have whatever I need. I'm going to underline in red my reactants and in blue my products. I need to do the same thing. Here I have a reactant. For oxygen, I'm going to leave it aside because it's in multiple places. And then I have my products, which is carbon dioxide and water. So first thing about my reactant, C2H6O, I need it to be on the opposite side. So I'm going to multiply it by -1. Okay, I'm going to get C2H6O plus CO2 will give me 3CO gas plus 3H2. Next, here, I have 2 carbon dioxide, so I need to multiply this by 2. I get 2CO plus O2 will give me 2CO2. Then I need to have 3 water, so I multiply this by 3. What do I get? I get 3H2 plus 3 over 2O2 will give me 3H2O. Okay? Now what do? I cancel. What can I cancel? I can cancel H2 and H2. Then what do I have over here? I have 3 carbon monoxide with... Oh, but now I notice I have a problem. This will not cancel with this. I'll be left with 1 carbon monoxide. So instead of multiplying by 2, I'll instead multiply by 3. So this becomes 3. 3 over 2, 3. Now, let us see. Let's check it properly. This cancels with this, right? Now, on top of that, what do I have? I have 3 CO2 here and CO here. So this will go bye-bye. This will get cancelled. And here I will be left with what? I'll be left with 2 CO2. So this I multiplied here by 3. Perfect. And now you add the O2s. Now combine everything together. You'll have C2H6O plus 3O2 will give me 2 CO2 plus 3 H2O. That's my answer. So what am I going to do? I'm going to multiply this by -1, multiply this by 3, multiply this by 3. So minus 254.4 times -1 plus minus 283 times 3 plus minus 286 times 3. What will this give me? This will give me as an answer. Let me check the answer key. Approximately minus 1.45 kilojoules. Minus 1.45 times 10 to the power of 3 kilojoules. joules. Okay, so that's my answer for question 21. We'll move on to question 22. Write the equation that represents the atomization of fluorine. Very simply, you have X of an atom, right? Usually they will give you in like the standard format. So let's say I'm gonna say whatever. This is for example, it could be solid, liquid, or gas. Will give me what? Will give me a single atom of what? Of the thing, right? So fluorine in this case is what is F2. So F2 gas should give me a single atom of fluorine as a gas, right? How do I do? What do I do to get the answer? I multiply here by 1/2. So it becomes 1/2 F2 gas. Will give me what? It will give me F gas. So that's it for this video. Thank you guys for watching. I hope you enjoyed and have a